Good morning, good afternoon. This is the second lesson on linear inequalities. And in this lesson, we are going to look at what are called compound inequalities. So these are inequalities that come in what we would think of as being two pieces. So they are called compound inequalities. If you think of chemistry class, those of you that have taken or are taking chemistry, you have atoms and then you have compounds. Compounds have like more than one thing in them, so a compound inequality has more than one piece to it. Now they're generally filed under two headings. You can have and inequalities and you can have or inequalities. We're going to take a look at the and inequalities first. Those I think are the easier of the two to deal with. And then we'll look at the or, and then we will see about doing a application problem to practice with. To begin with the ands, I'm going to use an illustration that just deals with numbers. And this is departing from the provided notes because I am splitting the lesson. So there's a little bit more time to deal with. And I think this might make some more sense if we just look at this with numbers before we introduce algebraic expressions. If you look at this statement right here, it says 2 is less than 3. And I think we can all agree that that is a true statement. And also, 2 is greater than 1. On the number line, whenever we're talking about less than, we're talking about numbers to the left. So 2 is less than 3 is a way of saying that 2 is to the left of 3 on the number line. And 2 is greater than 1. Well, greater than can be represented as to the right. In other words, 2 is to the right of 1. You could also think of that as saying 2 is between the 1 and the 3. So you could take that expression and you could write it this way. 1 is less than 2 is less than 3. That's what we mean when we say a compound inequality. Instead of writing two separate inequalities, we write one inequality that represents both of them. Now take a moment and look at this. You can see that this inequality, the 2 is less than 3, is right here in my compound. 2 is less than 3. Over here, it says 2 is greater than 1, but if you were to read it from right to left, you would read 1 is less than 2. Look at the direction that the inequality symbol is pointing. It's pointing to the 1 and opening to the 2. It's still true down here. We've just flipped it around. The inequality is still pointing towards the 1, and it's still opening towards the 2. And so what we've managed to do is write those two inequalities in this one statement. So let's take a look at an example using an x. Suppose I had this. X is greater than 4 and x is less than 8. Take a moment and think about whether or not both of those can be true. Can x be greater than 4 and also be less than 8? Let's take a look at it on the number line. Here's the 4, here's the 8. Is it possible for a number to be greater than 4, that means to the right, and also be less than 8? Yes, it is possible, and it would be represented by this piece of the number line. Those are numbers that are greater than 4 and also less than 8. That gives you an idea of how this and type of inequality works. So let's take a look at this one. Let's say 2x plus 1 is greater than negative 3 and 2x plus 1 is less than or equal to 5. Okay, so we have something greater than negative 3 and less than or equal to negative 5. Let's take a look at our number line. Just try to picture that. Number line is incredibly useful, and I don't think we use it as much as we could. There were some classes that I took in grad school especially. I would not have survived them without number lines to picture where things are. So the only numbers I put on there are the negative 3 and the 5. And this quantity, 2x plus 1, is greater than negative 3. So it's to the right of negative 3. And it's less than or equal to negative 5. Or, sorry, positive 5. Meaning it is to the left of positive 5. So it would be somewhere in here, greater than negative 3 and less than or equal to 5. Make sure you know why you either fill in the circle or don't. And the 2x plus 1 is sandwiched in between those two numbers. So you could think of it as 2x plus 1 is in between negative 3 and 5. Now, most of the time when you're dealing with an and inequality, you don't actually write it in two separate statements. And the reason for that is because it's extra work. I could take those two separate statements and do what I did over here with the 2, the 1, and the 3. I could take the two statements and write them as a single statement, picturing the 2 in between the 1 and the 3. So I'm going to do that here. I'm going to take the 2x plus 1, and I'm going to write it in between the 5 and the negative 3. I probably should have said negative 3 and 5. I don't know why I went from right to left there. And this is called a compound inequality. It's got the two pieces to it. Now, to solve a compound inequality, you solve it exactly the same way that you solve equations. So from this point on, all of this is the same as what you know before. I'm going to do a little picture illustration on the next slide just to rationalize what we're doing, like why the operations still work the same. When we're solving an equation, we know that it's like having a little balance scale where whatever's on the left side of the equal sign is equal to whatever's on the right. And so we want to keep it balanced. That's what the equal sign represents. And that's why we do the same thing to both sides. And in inequality, it's tilted. You have one side being greater or less than the other side. But suppose I have some stuff here. And we're going to have some stuff on here. So I have like 3 yellow dots and they're outweighing the 2 blue dots, and that's why it's tilted. If I want to perform an operation to my inequality, I want to isolate the x, I cannot just take away a dot from the right-hand side. If I only take away a dot from the right-hand side, I have now accidentally balanced my expression here, inequality, and it's now an equation because now I have the same amount on both sides. If I wanted to take away one of my yellow dots from the right-hand side, I have to make sure that I take away one of the blue dots to make sure that it stays unbalanced in the right way. If I start taking away stuff from one side, okay, so I decide to take away 2, now it's actually unbalanced in the other direction. So the same principle that guides us solving equations also guides us solving inequalities. In other words, whatever you do to one side, you have to make sure you do to the other side. So let's bring that back to this problem here. The only thing that makes this a little bit different is instead of just having 2 sides, it's like I have 3 sides with this kind of chained inequality. But the principle is the same. Whatever you do to get the x by itself, you've got to do it to the other side of the inequality. It's just, in this case, it's to the left and to the right. So I want to get the x by itself. We go through this the same reasoning that we do for an equation. We think what's happening to the x? It's being multiplied by 2 and adding 1. How do I undo adding 1? I subtract 1. I can't just subtract 1 from the middle though. I have to make sure that the other 2 pieces come along with it. So, and then watch your signs here. Negative 3 minus 1 is negative 4. In the middle here, 1 minus 1 is 0, and that's why it drops out. And then 5 minus 1 is 4. And just like with an equation, if I have 2 times x and I want to undo the multiplication, I would do division. And just like with an equation, you would have to do the same thing. It's just in this particular problem, you have 3 of them to do. Negative 4 divided by 2 is -2. 2 divided by 2 is 1, leaving us with the x, and 4 divided by 2 is 2. Just you might have noticed I was a little bit slow in putting my equal sign there. Just be careful. It's easy to drop that. You just watched me drop it, so be careful. And then that's the end of the problem. So x is between -2 and 2. If you were asked to graph this, all I would want you to put on your number line is the -2 and the 2. And the -2 side is going to be an open circle. The 2 side is a closed circle. And the x is in between it. So we would shade in between. And that's the first type of compound inequality. Second type of inequality is that OR type. And this can get a little bit dicey. We want to be careful. Just suppose for a second, I just want to make sure that you understand the difference here. I can say that x is greater than 4, and if I put the word "and" here, x is greater than 4 and x is less than 2. I want you to stop and think for a moment if that's possible for x to be greater than 4 and less than 2. Greater than 4 is over here to the right. Less than 2 is over here to the left. Is it possible to pick a number that is both of them? Because that's what "and" means. It's both. And the answer to that is no. That's actually an impossible statement. So you want to be careful and make sure you don't accidentally use the word "and" there. But what I can do is I can put the word "or." I can say x is greater than 4 or x is less than 2. If I were to graph that, okay, the graph would look the same as what I just did. X is greater than 4 or x is less than 2. So it can be one or the other. It can't be both. So we have to use the word "or," not the word "and." And I could, basically any value of x that would be in this region or in this region would make the statement true. Notice that it's the flip-flop from the one we just did. When you have "and," it's sandwiched in the middle. "Or" means you have two separate regions and you can be in one or the other, but not both. So let's look at the problem from the notes. We have x plus 3 is greater than or equal to 5, or x plus 3 is less than or equal to -5. And you have to keep them separate because it can't be both greater than 5 and also less than -5. So these ones are actually solved separately. The "and" ones, we combine them into one statement, but the "or" ones have to stay separate. You can't combine them, and I'm going to say a little bit more about that in a moment. This is pretty straightforward to solve. I have a plus 3, so I know I would undo that with subtracting 3. So x is greater than or equal to 2, or x is less than or equal to -8. And then when you go to graph it, all I care about is that you just have those two numbers. So less than or equal to -8, less than is to the left, or greater than or equal to 2. And that, of course, would have the solid circles. So that's the other type of inequality. Now, I want to point out something. This is a very, very common mistake. I teach a couple dual enrollment math classes, and my students in dual enrollment, and they've all had Algebra 2 to even get to dual enrollment, they will make this mistake. They will see x is less than 2 and, not and, or x is greater than, 4, okay? And that's okay. X is less than 2 or greater than 4, like one or the other. But what they will try to do is they will try to put that into one statement, and you can't do it. They have to stay separate. So they will try to do something like this. Write this. Now, that's the same as this statement right here. This says X is greater than 4. This says 4 is less than X. But that's the same thing. It's like saying 1 is less than 2. 2 is greater than 1. And notice the sign, even though it flipped, it's still pointing the right way. So it's pointing to the 4, pointing to the 4. Then they'll try to merge that with this and say X is less than 2. And they're like, oh, this is great. Like now I can just solve it. And I took my or and I wrote it as a compound inequality. I would like you to, if you're doing this at home, pause for a moment. In class, I'll give you a moment to think about this. What is wrong with this statement? So take a moment and think about that. If you look closely at this statement, it is actually a false statement. Now remember, X is a variable. X is a number. It's an unknown number. If I ignore the X for a moment, what we actually have, and then like we kind of have an extra one, what we have written here is really 4 is less than 2, which is not true at all. And so if you take an or and you try to combine it into one statement, you actually end up with a wrong or false statement. So you don't want to do that. Here's a couple of other things I want you to be on the lookout for. Always write your inequalities with if you're going to combine them together using less than. It's not mathematically incorrect to write it the other way around, but because our number line works from less to greater, it is logical and comfortable for us to put the smaller numbers on the left and the larger numbers on the right. I can't mark you wrong for doing it the other way, but it's better if you do it this way. Here's a couple things that should never happen. Okay, we're going to never, ever, okay? You should never in a compound inequality have your symbols flip-flopped, okay? I'll see that sometimes and I'll see that. Okay, they should always be facing exactly the same direction, preferably less than, but you should never have like one less than and one greater than. That should never happen. If you're doing your homework and you've written something like that, you have made a mistake. Probably doing what I said not to do. You've probably taken an or statement and tried to combine it into one. It's the and ones that can combine. And I think as long as you're careful about that, you should be okay with the compound inequalities. I don't know. Wait, why is that off? Oh, okay. Hold up. I don't know what's happening here. Okay. I think we're okay now. All right. So we have an inequalities application problem here. Inequalities are more common in real life than equations are. Actually, most of the relationships that we have, that we deal with in the real world are inequalities. And I'll do some scratch work here. If you wanted to make a B in Algebra 2, what grade would give you, what numerical grades would give you a B? It's not just one grade that would give you a B. A B is anything in between an 80 and an 89. And so if you wanted to get a B, there's the range of numbers. So we're actually quite familiar with inequalities and with compound inequalities in our everyday lives. If you are old enough to drive, you know that you have a speed limit. If the speed limit is 30 miles per hour and you're going 25, you're fine. Cops are not going to pull you over for that. But if you're going like 60, you'll have an issue. That's another inequality. And then sometimes on the highways, there actually will be a minimum speed limit as well. And that would be that compound. So here's our application problem. The budget for a school field trip is $500. It costs $220 for the bus plus $7 per student. How many students can attend the field trip? This is assuming the school is paying for the field trip. So if the budget, we'll use some annotating skills here. Okay, I'm going to underline. The budget is $500. That means that the cost of the trip has to be less than or equal to $500. We can't go over it. We can stay under it. The school bookkeeper is not she's going to be totally okay if you come in under budget and you have extra money left over. What you can't do is go over it. So the cost has to be less than or equal to $500. There's the inequality. Now, what is the cost? Well, it's $220 plus $7 per student. So I'll use an S. Be careful when you're using an S as a variable because it looks a little bit like a 5. And that sets up our inequality. So $220 plus $7 per student has to end up being less than $500. So the rules for this are the same as for solving an equation. We want to get the S by itself or solve for S. This is a positive 220. And I want it to go away. In other words, I want it to end up being 0. So 220 minus 220 is 0, leaving me with 7s. 520 minus 220 is, or 500 minus 220 is 280. And then that's multiplication. Do I need to flip here? Nope. Whoops. Because that's, there we go. Because that is a positive number, so you do not have to flip it. And the solution is S is less than or equal to 40. So 40 students can go on this field trip. We can take fewer than 40 students, but we cannot take more than 40 students. And there's our example word problem. So that completes our lesson on linear inequalities.